Okay. Right, so this is a review for what we did last week, in case someone wasn't able to make it. We defined what a multi-qubit state was. Defined that using a tensor product. This was an example here is shown for 2-qubit tensor products. It's basically the same as multiplication, except you also remember the state it came from. You should note that some states cannot be written as a product of two smaller states, states with a smaller number of qubits, and these are known as entangled states, and these are very cool states. We'll be looking at some examples of how to use these today. For example, this state here is called a Bell state. This is a Bell state over 2 qubits, and there's a few more of these, but this is the main Bell state which we'll be considering, especially in this lecture. Quantum gates are linear operators, that are also unitary, and by unitary I mean its inverse is its conjugate transpose. So U inverse is U dagger, which we denote by this notation here. And what this means is you just take the transpose and you take the conjugate of every element. We defined what the quantum circuit was. Formally, we didn't look at this last time, but the formal definition is, which we consider as a finite sequence of unitary gates applied on a finite set of qubits. And we looked at how we can walk through the action of a quantum circuit last time, and we'll use that this time as well. But most importantly, we defined the notion of measurement, and in case we weren't able to spend enough time looking at it last time, here's one way to think about it. So we defined the measurement to be a sort of projection operation. So if you have a state that is in this form, and the probability of measuring a 0 in this state is you get it by looking at dropping a perpendicular to the 0 state and then considering the proportion of the amplitude over here squared. So for example, you can write any state psi in the form of alpha 0 plus beta 1. Since the state is normalized without loss of generality, we can let theta be a real angle such that the magnitude of alpha is cos theta and the magnitude of beta is sine theta. Can someone remind me what the probability of measuring 0 in this state would be? Yeah? 50%? Not quite. If you have the state given as alpha 0 plus beta 1, then we define the probability of measuring 0 to be the magnitude of alpha squared, which if we define theta to be such that the magnitude of alpha is cosine of theta, this evaluates to cos squared theta. Right. So for example, here's a state which will show up later on. If you have psi equals cosine of pi by 8, also this is in radians. We'll be working with radians throughout this course. Here's just a refresher if someone is unfamiliar. If you have this state, what would the probability of measuring, say, a 1 be?
Sine squared pi, right?
Yes. Right, so in this case, we write the probability of measuring 1 as sine squared pi over 8. So a visual depiction is obviously useful. You can represent it by drawing, say, a perpendicular like this. In the case where the coefficients are all real numbers, this is very useful. Otherwise, you can define theta to be satisfying this in the basis, and then dropping the perpendicular appropriately. So, for example, consider this theta once again, but instead consider the plus minus basis. As a reminder, the plus minus basis, you can express it as follows. Here, this angle would be pi by 4, because if you remember, plus was 1 over square root 2, 0, plus 1 over square root 2, 1. What would the probability of measuring psi in the plus state be, given using this sort of visual analogy?
You project psi onto the plus vector, and then what are the components areas?
Right, so an easy way to remember this is if you draw this perpendicular line, the angle it forms, this angle, you should take the cosine square of that angle, and that will be your probability of measuring that particular outcome. Don't worry if this is a bit confusing. We'll look at this in more detail soon. But so far we've only been considering simple quantum circuits and what the measurement is. And today we look at some early forms of quantum algorithms. Namely, we'll look at the Hadamard test, and then we look at some cool applications of the Bell state, which we found earlier, to show that nature is not purely classical. Now, I mentioned earlier that we covered how to walk through quantum circuits. Here is a sample quantum circuit, and just as a refresher, we'll walk through the action of this circuit. So let psi be the input state alpha 0, beta 1. Also, as a question, can everyone see the bottom of the board? Okay. Right, so what would the action of the first H gate be? Like, this is how we define walking through the quantum circuit. If you have an H, if you have a Hadamard, yeah?
Applying it into the plus state?
Yeah, exactly. So you start with the 0 psi, you apply a Hadamard, you go into the plus state, tensor psi. Then you have a controlled knot, which, if you remember, it's do this operation if and only if this is in the one state. So we get the following state here. Come on. Okay. So if this was 0, psi gets carried over directly. But if it was 1, we flip the bit psi, because that's what the X gate does, if you recall from last lecture. And then we have another Hadamard, and it's if you just apply the Hadamard, if you remember that quantum gates are linear, you can apply it directly to here, to this state here, and also to the other state here. And you get this long expression, which you can simplify down into this form over here. This is just math simplification, so it might look a bit tedious, but you just apply the Hadamard operator to the given quantum state directly. Now, more generally, I claim that if you have any unitary operation U in this circuit, recall earlier that we had the special case where U was the X gate, the Pauli X gate. If you have this, then this creates the state which is 1/2 0 tensored with U plus identity plus 1/2 1 times identity minus U. And if you look at this, just as a sanity check, just to make sure that I'm not lying, you can write this state as alpha 0 plus beta 1 plus alpha 1 plus beta 0, which is indeed identity plus x applied to the state psi. So it's always useful to do these kinds of sanity checks in the middle. Right, so this forms, this circuit here will be a very recurring theme for us as we go on in the next lectures. Basically, if we have a circuit which does a Hadamard in the beginning, and then some weird stuff over here in the middle, and another Hadamard to wrap up the circuit, this will be a very, very key fundamental building block for many more quantum circuits later on. Even more generally, and I leave this as an exercise to verify, you just walk through the quantum circuits, and here the open circle means do if and only if state is 0. So it's the opposite of this. Here we do it if you are in the 1 state, and the other you do it if it's in the 0 state. This circuit, I claim, it prepares this state, which is U plus V in the case of 0, and U minus V in the case of 1. Now, this result is a very crucial result. It's called Hadamard's lemma. And the reason why it's important is, suppose at the end of this outcome you measure a 0 in this qubit, what would the resulting quantum state be? So again, you have 1/2 0 times U plus V times psi. And also, don't worry about normalization for the time being. And you have a 1 times U minus V psi. So if you measure 0, it's equivalent to projecting it and considering only the states where the first qubit is in the state 0. So once you measure 0, the outcome would be something which is a normalization of U plus V over 2 applied to psi. And if you do the normalization, well, you will see that this is actually square root 2, but that's fine. So this gives us a way of adding together two operations on a quantum computer, which is something very non-trivial, because you might realize, as I claimed earlier, any operation can be written as a sum of these gates, and if you can form the sum of U plus V applied to psi for any unitary U and V, that's a very powerful computational resource to have. Now similarly, if you measure 1 here, Any takers for what the state would be? Yeah.
U minus V over, divided by 2 or square root of 2.
Yeah. It would be something proportional to u minus v applied to psi, and the proportionality factor is just 1 over square root of 2. Again, you should verify this for yourself. You should never take stuff at face value, and you should always assume that the other person is lying. Now, here's the first algorithm which we'll consider in this session. Okay?
Could you be lying that you're lying?
Good question. Think about it. Right, so here, this is a very standard model for what a quantum algorithm looks like. In a quantum algorithm, you very rarely get the correct answer with 100% probability. There are some cases where that happens, but usually what you will have is something called an error tolerance, which is how far you can be from the error and how much error you can tolerate, quite literally. And what this means is if the correct answer was, say, some gamma, then we can if the algorithm outputs gamma tilde such that we are not too far away from the correct answer, then we are okay with it. Now, I claim that the Hadamard test does the following. You run this circuit over here, and at the end you have the measurement operation. Now, if you measure a 0, I say that you should output a 1. But if you measure a 1, then I say you should output a negative 1. And then I say you should repeat these two steps for some, say, n over epsilon squared times. And you shouldn't really worry about why we repeat this many times. That just comes down to a matter of statistics, and which says that if you want to sample something, then you just run some analysis on how many times you should repeat. But don't worry too much about this repetition step. But the important thing is you should keep a running tally of the sum of the outputs. Now, that's a very cool algorithm, yeah, but I guess the important thing is what does it do? I didn't specify that, but let's look at it. So suppose the output you denote it by some random variable x, and you want to find what the expectation value of this x is. Okay, so first to do that, you should note that you can write the expectation value of x as the probability of measuring 0 times the value which x takes if you measure 0, that is plus 1, plus the probability of measuring 1 times the value which x takes if you measure 1, which is negative 1. Now, what is the probability of measuring 0 here? Well, you just run through the circuit again. Hopefully, if you had it copied down, that's okay. If not, here's the circuit. Right, so from Hadamard's lemma, okay, and I guess we are considering the general case, so this is some u. And applying the projectors, you get the probability of measuring 0 is technically it's 1 over 2 psi identity plus u dagger, and from the first session, this is just a matrix product which gives back a real number, if you remember that. In the end, this will output some value. This will just be some value. Also, oops, there shouldn't be a dagger there. And if you just run through the steps and note that here u dagger u is the identity because u is unitary. The probability of measuring 0 is given by this expression here. So let's walk through the steps. So first we just expand out taking the conjugate transpose inside the bracket, and then you just do the matrix multiplication step. You expand out the product like this. Then you use the fact that u is unitary, and then since this is just matrix multiplication, this is linear, so you can split out the terms, and the 2 over here cancels with the 4 to give us a 1/2, and you get a u plus u dagger on the other side. And since psi was a normalized state by assumption, this is just 1, and this is how we get the answer. So similarly, I claim that the probability of measuring a 1 is very similar to this, except instead of a plus here, you have a minus here. And then we now have all the resources we need to compute the expectation value of x, which we define like this. So the output over here, what this gives us in the end, is just the real value of psi u psi, and this is a term which we will define to be the expectation value of u applied to state psi. And then the repetition of, say, order of 1 over epsilon squared twice is just to get this within an epsilon, and we don't need to worry about this, except for the few statisticians among us. Please don't come after me if I don't know enough statistics. Okay, so as an exercise, you should try to also compute, similar to how we computed the real value of psi u psi of the expectation value. You should also try to compute the imaginary value. And to do this, I claim that we only need one more y gate in the Hadamard circuit, and well, there's only so many places you can put the y gate. So just try to find where the right place would be. But if you do this, the nice part is, if you can compute both the real part and the imaginary part of the expectation value, you can add them up. To get the complete expectation value. And notice that this is a non-destructive way of measuring the expectation value. We did not affect the state psi in an irreversible way. That is to say, we did not conduct any measurements on the state psi. And the application, like whatever whatever way in which we affected state psi, we did so reversibly, so we can recover back the original psi. That is to say, in this circuit, the only measurement was done on the first qubit, not on the second quantum state. So this is a very powerful approach, which allows us to reversibly extract information from our quantum states. I was planning on covering this, but I think we could just leave it as, say, something to verify. I claim that there is no unitary operation U which can effectively copy a quantum state onto another quantum state. So if you have an empty state 0 and some other state psi, there is no quantum gate or quantum operation or quantum circuit which can do this operation over here. And the proof of that is, suppose you can, and just show that it messes things up, basically. But yeah, okay, so now let's play a game, shall we? No, really, let's play a game. I am not kidding. Let's have, say, 3 parties, Alice, Bob, and Charlie. And the game is as follows. So Charlie generates, say, 2 numbers, x and y, from 0 and 1. So x and y could be either 0 or 1, randomly and independently. Charlie gives x to Alice and gives y to Bob. And the only communication between Alice and Bob is allowed before this step, so before they get the bits. Once they get the bits, they are not allowed to communicate amongst each other at all. Alice gives back a number A to Charlie, and Bob gives back a number B to Charlie. And Alice and Bob win when the product x times y is equal to A plus B mod 2. So that is to say, if x and y are different, then A and B must be the same. Otherwise, if x and y are both 1, then A and B must be different. And if x and y are both 0, then A and B must be both the same. So here's what the desired outcome of A and B should be if Alice and Bob must win. This should be a 0, a 0, 0, and a 1. Okay, so let's play a round of this game, shall we? Do I have any volunteers?
Sure.
Oh, I guess there's only one pen.
I have 2 more pens.
Okay, whenever you're ready.
Who's down to 2 balls?
I think it'd be Alice.
I'll be Bob.
Wait, was there a strategy there that spoiled the game? Below? Scroll down.
If you didn't see it, too bad. Okay, I say x is, wait, okay. Now this goes back. There's no way to do this without revealing it on the board, but okay, so I say x is 0 and y is, say, also 0. What should we, like, just write that out and hold it up, I guess, so that you can't communicate.
Could you check the win condition again? Also, okay, I guess it's right there.
Wait, we have to find A and B or A plus B?
Alice gives back A, Bob
Okay,
gives
okay,
back B. Okay. Bob, what's your
I now
0? unfortunately you didn't win.
No, we got it.
Okay, so if you can.
Wait, but there is an equation that says that 0 equals 1 that exists.
Sorry?
There's an equation that says that 0 equals 1 I remember seeing.
Where was this?
It's a neat little trick that one can do with math. Just Google it. 0 equals 1.
0 equals 1.
Well, it depends on the ring.
It depends, it depends on how you define additions. Or not in the case I'm usually familiar with, so. And I'm Charlie, so I guess I get to decide who wins. Okay, so classically, I guess the best strategy for Alice involved is to always guess 0 or to always guess 1. With this strategy, you have a 75% success, because if you do this, note that a plus b will always equal 0. And note that whatever x and y are, if a plus b equals 0, you have a 3 out of 4 chance of winning. So that's a success rate of 75%. Now I say that this is the best strategy which you can have, and it's not too hard to see why. You have only 4 possible options of what you want, and since A and B cannot communicate between each other, their inputs, the output A and the output B can only depend on what X and Y are. So they are functions of one bit. So you can have only 4 such functions between 0 and 1 and 0 and 1. And if you just work your way to brute force, you can see that these two are the best strategies. So classically, there's no way of improving on a 3/4 success probability. But I claim that using quantum entanglement, you can get the success probability boosted to cosine squared pi by 8, which is approximately 0.85. And if this is ringing a bell, sorry, that was not intended. If this seems familiar, it's because of this example here, where we did cosine pi by 8 and sine pi by 8, which is, we'll be playing on sort of a similar reasoning right now. So before we get to that, we should first, we will build up to this result by looking at how the Bell state behaves, and by basically showing that it's got some nice properties. So first of all, remember that we define the standard Bell state to be 1 over square root 2 0 0 plus 1 over square root 2 1 1. Any ideas for how we can prepare this state? Starting, if we start from the 0 state, what should be the first operation we do? Remember we've only discussed one type of circuit so far, so.
Is it Hadamard?
Yes! When in doubt, you do a Hadamard. 99% of the times, the first gate in your quantum circuit will be a Hadamard. The only 1% of the time, it will not be a Hadamard. The second gate will be a Hadamard. Okay, and then what do we do? What comes next in the fundamental circuit design which we looked at so far? Yeah?
C naught?
Yes! Exactly. So more generally, you would have a control some unitary, but in this case, the C naught works perfectly. Let's walk through the circuit. Let's see what happens. So you start with 0 0. After applying the Hadamard, you have 1 over square root 2 0 1 plus 1 over square root 2, sorry, 0 0 plus 1 over square root 2 1 0. And after you do the C naught, you get the Bell state as desired. Now, this should seem fishy to you, or I mean, at least it did to me, but we claimed earlier that you can't clone a quantum state. But isn't that what we're doing here? Is this not the thing? We are cloning the 0 here and we're cloning the 1 here? What's up with that? Any guesses? Yeah?
Well, isn't the line a representation of time instead of an actual circuit? So it isn't like you're actually like cloning it, you're just going from time and changing it?
I mean, isn't that what cloning was? Like, if you at some point you have some state psi and you have some state 0, after a certain amount of time, like you need time to apply a quantum operation. So isn't that what cloning was? But that was a good try. That was a good try. Yes. Basically, I lied. We are not cloning here because this is not. This was a slight trick. This is actually the state 1 over square root 2 0. This 1 over square root 2 1 applied to like tensor with 0. And even if we could replicate this, I mean, yeah, you can clearly replicate this, right? Like you can clearly get the same state here. The important part was you cannot clone arbitrary states. So if you have, say, an unknown state psi, like over here, and again this goes back to the very first session where I discussed that the state of this is actually known. It is exactly 0 plus 1 over square root 2. So you cannot clone an arbitrary quantum state, but if you have a known quantum state, you can prepare it in most cases. And although the preparation might not be short, it might be very time consuming. But anyways, that's how you prepare a Bell state. It's a very simple circuit, and it subscribes to the quantum design which we've looked at so far. Now, in the 1930s, Einstein, Podolsky, and Rosen, three physicists, posited a paradox which said that local realism exists and it governs nature. So basically, what they were saying is, if you measure the first qubit here, surely you need some time before it affects the second qubit here, right? Because, for example, if you measure the first qubit in the 0 state, the second qubit is automatically collapsed to the 0 state as well, based on what we've been looking at so far. And it was 30 years that this riddle remained unanswered. And in 1965, Bell came up with a thought experiment, which is precisely the game which we were playing earlier. So, yeah, about 60 years ago, you could publish games and you could win prizes. So, sucks to be born in the modern era. Which stated that, you know, if nature was classical, you could win with at most 75% probability. That is what the E here stands for. But according to the principles of quantum, you could win with more than 3/4 probability. And to see that, we look at another important property of the Bell state. And this relates to the cartoon diagram we were looking at earlier in the 0 and 1. So I claim that the Bell state is rotationally invariant, which is a very fancy way of saying that instead of considering 0 and 1, you consider some other perpendicular normalized vectors, u and u port, which look something like this. Consider any such u and maybe I'll just draw u perp down, but you could also take u perp up above, that wouldn't matter. If these are both normalized and still perpendicular, the Bell state remains the same in this representation. So more formally, for any orthonormal vectors u and u perp, if you look at the Bell state psi given by 0, 0 plus 1, 1, you can write it as uu plus u perp. And the important restriction here is that u and u perp must be written in terms of 0 and 1 as real sum. You can't have complex sums. So recall earlier that we defined quantum states to be a quantum linear sum of 0 and 1. But in this case, we are not allowing that. Because if we did, you could say that any state is a Bell state, which is clearly nonsensical. So given u is a0 plus b1, you can then write, say, up to plus or minus. You could write u is b0 minus a1, or equivalently, you could also write minus b0 plus a1. Both of these work. Also, since u and u perp are normalized, we require this condition. And this, you can see, is very related to what we were discussing earlier. By writing any state psi as alpha 0 plus beta 1, but in this case alpha beta were complex numbers, not real numbers, and that's where the difference comes in from. Now, anyways, the proof for this is just computation. You just substitute this in, you find what 0 is and what 1 is, because this gives us a simultaneous system in two variables, and you can solve this easily by just adding and multiplying. And oh dear, yes, I know my license has expired. No. Okay. I'll just leave this as computation to be verified. Again, don't trust me blindly. Work through this yourself and convince yourself that it is true. Anyway, so here's a quantum strategy. I said earlier that Alice and Bob cannot communicate once the game starts, but they can communicate before the game starts. That is how we got the strategy for letting both Alice and Bob respond with 0 or both responding with 1. So they can fix strategy beforehand. They can also share resources, like sharing homework beforehand. You should not do that in any of your courses, by the way. Just a warning. So in this case, let's say Alice and Bob share a Bell state. 1 over square root 2, 0, 0, plus 1 over square root 2, 0, 1, 1. And say this is Alice's qubit, this is Bob's qubit, and same over here. Now, here's what Alice does. If Alice receives input from Charlie as x equals 0, then she immediately measures her qubit in the 0, 1 basis. No? Otherwise, Alice applies a Hadamard, and then she measures her qubit. And graphically, you can represent this by saying you can measure this. If Alice receives a 0 as her input, she measures in the standard basis, the standard computational basis. Else she measures in this rotated basis of the plus and the minus state, as we looked at earlier. And this forms an angle of pi by 4 with the computational basis. Now similarly, what Bob does is if he receives as input y equals 0, then he measures in this basis which forms an angle of pi over 8. I should enlarge this. With the computational basis. Otherwise, if he receives an input of 1, he measures in the basis which forms an angle of minus pi by 8. Again, at this point, I should also convince you that these measurements are realistic. You can actually measure in these bases. But to do that, I'll do what everyone does when they're bluffing, and I'll leave it as a claim. The claim will be that these are the, this are the eigenvectors. Again, if you represent these as both column vectors from what we discussed in the first session, these are the eigenvectors of the operator z plus x over square root 2, and these are the eigenvectors of z minus x over square root 2. Now, you could do the honorable thing, which is you could compute out the eigenvectors yourself, or you could just plug it into eMath help or Wolfram Alpha or whatever. As a reminder, z plus x over square root 2, you can evaluate this to 1 over square root 2, 1 over square root 2, 1 over square root 2, minus 1 over square root 2. And does that look familiar to anyone? Does that matrix thing? Well, this is just the Hadamard matrix. But in any case, you can prepare these states as well. So this is only showing that these are the eigenvectors of some unitaries. So this, if you label these as U0 and U1, since these are the eigenvectors of some unitary matrices, you can prepare them in practice, although I won't give the preparation right now. But let's move on to the proof of why this gives us the optimal, like the success rate for this is greater than 3/4 in the limited time we have. So we consider 4 cases as follows. We consider x0, x1, y0, and y1. And we'll consider the basis in which Alice and Bob measure in. And we'll only consider what 0 is represented as, because the case for 1 is very similar. So this is the case for x0. This is the case for y0. This is the case for y1, sorry, x1. And this is the case for y1. And these are all angles of pi by 8. Now, in 3 out of the 4 cases of x and y, Alice and Bob win if their answer is the same. If you remember, a plus b must be 0, 0, and 0 for Alice and Bob to win. And this is only achieved if a equals b. So in these 3 cases, we want the results output by Alice and Bob to be the same. So let's go through them. So if you have x0 and y0, the angle that the measurement outcomes are the same are precisely cosine squared of this angle, if you remember from earlier. And what's this angle? This is precisely, okay, if we, my bad, same, cosine squared of pi by 8. Again, if you consider what x0 and y1, if you consider the angle between that is this angle, and that's just cosine squared of negative pi by 8, which is equal to this. And similarly, if you consider the angle between the outcomes x1 and y0, that is this angle here, which is also cosine squared of pi by 8. So in all three of these cases, the probability of Alice and Bob winning is cosine squared pi over 8. And in the last case, 1 and 1, Alice and Bob win if their output sums to 1, which only happens if they have the different result, if A and B are not the same. And this occurs if you have, say, say x1 and y0. Sorry, if Alice and Bob output a 1 and 0, or they output a 0 and 1. If you look at the probability, you will also get cosine squared pi over 8. And then by summing over all of these probabilities, remember that x and y were drawn randomly. So each of these 4 cases is equally likely. So the probability of Alice and Bob winning is just 4 times 1 over 4 times cosine squared pi by 8, which is precisely cosine squared pi over 8, and this we know is strictly greater than 0.75. So it's an improvement over the classical case. So too bad you guys didn't share this. Right, so sorry I went slightly over time. I didn't have a worksheet out last week because we didn't cover much stuff last week. But this week I'll send out a list of practice problems which will hopefully help clarify some things.
To go find out how many times you're going to repeat the experiment. That sounds weird.
So that was the conducted in experiment.